Somewhere in the universe, right now, there is a place where the laws of physics, as we understand them, simply stop working. A place where gravity has become so extreme that nothing, not matter, not energy, not even light itself, can escape. A place where space curves back on itself so completely that the concept of outside ceases to have meaning. A place where time, according to our best mathematics, slows and stretches and eventually reaches something very close to a stop. We call it a black hole. And for most of human history, it existed only as an idea, a mathematical ghost, a strange solution to an equation that physicists found both beautiful and deeply unsettling. For decades, serious scientists debated whether black holes were real at all or simply an artifact of equations pushed beyond their limits. Then, on the 10th of April 2019, a team of over 200 scientists released a photograph. It was blurry by most standards, a smudged orange ring around a darker center, but it was the first direct image of a black hole ever captured. The supermassive black hole at the center of a galaxy called Messier 87, 55 million light years away. The world looked at it, and something shifted. Because the image didn't just confirm a scientific theory, it made real something that had lived, for most people, entirely in the realm of the abstract and the imagined. It put a face, of sorts, on one of the strangest objects the universe is known to contain. And wherever something strange and powerful and only partially understood exists, questions follow. Not just scientific questions, though there are many of those, but deeper questions, stranger questions. Questions about what black holes really are, about what happens inside them, about whether they might be something more than collapsed stars, doorways perhaps, or engines, or evidence of something about the nature of reality that the standard story of physics hasn't fully reckoned with. In the next 2 hours, we're going to walk through all of it. We'll begin with what black holes actually are. The science, the history, the genuine strangeness that even mainstream physics fully acknowledges. Then we'll move into the theories, the famous ones, and the fringe ones, the ones whispered in online forums, and the ones published in the papers of serious physicists who disagree sharply with their colleagues. We'll talk about whether black holes might be portals, whether they might be connected to the creation of new universes, whether the information they consume is truly destroyed or secretly preserved, whether some researchers believe black holes are not natural objects at all. And we'll look at the stranger edges, the theories about what our universe might actually be, and the role black holes play in those ideas. Some of what you're about to hear is the cutting edge of accepted physics. Some of it is serious scientific debate that has not yet been resolved. Some of it is speculation, beautiful and untethered, the kind that lives at the border between science and something else. All of it begins with a simple, vertiginous fact. There are places in this universe where everything we think we know reaches its limit. Let's start at the beginning. To understand why black holes generate so many questions, why they have become the single most discussed, most theorized, most mythologized objects in modern science. It helps to understand what they actually are, and to appreciate that even the official mainstream scientific story is, by any reasonable measure, one of the strangest things the human mind has ever worked out. Let's go back to the beginning. Not the beginning of black holes themselves, which predates human civilization by billions of years, but the beginning of the idea. The first moment a human being sat down and thought, what would happen if gravity became strong enough to trap even light? The first idea. The year was 1783. The place was England. And the person was not a professional scientist in a modern sense, but a Church of England clergyman named John Mickle, a man who, in his spare time, happened to be one of the most original scientific thinkers of the 18th century. Michel was interested in stars. He was, in fact, one of the first people to suggest that many of the stars we see in the night sky, exist not in isolation, but in gravitational pairs, what we now call binary star systems. He was right about that, and it took decades for the observation to catch up to his intuition. But in 1783, he published a paper containing a different idea, one that was so far ahead of its time that it sat in libraries largely unread for over a century. The reasoning was simple, almost elegant. Newton's theory of gravity was well established by then. It described a force of attraction that grew stronger as objects got closer together and weaker as they moved apart. Newton had also described light as a stream of particles, tiny corpuscles moving at a finite speed. Michel asked a quiet question. If light moves at a finite speed, and if gravity can slow things down, then is there a point at which a massive enough object could generate enough gravity to prevent light from escaping altogether? He did the calculation. He found that a star with the same density as the Sun, but roughly 500 times its diameter, would produce a gravitational pull at its surface strong enough to prevent light from leaving. He called such objects dark stars. The paper was presented to the Royal Society and promptly filed away. It was interesting. It was mathematically sound, within the framework available to Michel at the time. And then the world moved on, and the paper was forgotten. A French mathematician named Pierre-Simon Laplace independently arrived at the same idea a few years later and included it briefly in a popular astronomy book, then quietly removed it from later editions, possibly because he himself had doubts about whether it made sense. The idea of the dark star went to sleep. It would not wake up for more than 100 years. Einstein and the curved universe. When it did wake up, it was in a form that John Michel would barely have recognized. In 1915, Albert Einstein, then 36 years old, working at the patent office in Bern, Switzerland, and already the most famous physicist in the world, published the general theory of relativity. It is difficult to overstate how radical this theory was, and in some ways still is. Newton's gravity was a force, a mysterious pull between masses, acting instantly across any distance, with no explanation of how it worked. It was enormously successful. It predicted the motions of planets, the trajectories of cannonballs, the tides. For over 200 years, it was the foundation of mechanics. Einstein dismantled it. In general relativity, gravity is not a force at all. It is a consequence of geometry. Mass and energy curve the fabric of space-time, the four-dimensional structure in which all events occur, and other objects move along the straightest possible paths through that curved geometry. What we experience as gravity is not a pull. It is the result of following a curved path through a curved space. This is extraordinarily difficult to visualize, and that difficulty is honest. The geometry in question is not the geometry of ordinary three-dimensional space, but of four-dimensional space-time, which cannot be directly pictured. But its consequences can be tested, and they have been repeatedly with extraordinary precision. General relativity predicted that massive objects would bend the paths of light rays passing near them. This was confirmed dramatically during a solar eclipse in 1920, when stars near the edge of the sun appeared slightly displaced from their usual positions. Their light had been bent by the sun's gravity, exactly as Einstein predicted. The measurement made Einstein world famous overnight. General relativity also predicted that time would run slower in stronger gravitational fields, a phenomenon called gravitational time dilation. This has been confirmed in countless experiments, from comparing atomic clocks at different altitudes to the corrections that must be applied to GPS satellite signals every single day for the system to work correctly. The equations were, and remain, beautiful. They describe the universe in a language of geometry that feels, to those who work with it, almost inevitable, as if the universe had no choice but to be this way. And then, within weeks of Einstein publishing his theory, a young physicist in the trenches of the First World War found something inside those beautiful equations that troubled everyone who looked at it. Schwarzschild in the trenches. His name was Karl Schwarzschild, and in 1915 he was serving as an artillery officer on the Eastern Front, doing the grim mathematics of trajectory and distance required by war, while in his spare moments working on something entirely different. Schwarzschild was brilliant and meticulous. When Einstein's papers on general relativity were published, Schwarzschild obtained copies at the front and read them carefully. And then he did something that even Einstein had not been able to do. He found an exact analytical solution to Einstein's field equations. Einstein's equations describe how the geometry of space-time responds to the presence of mass and energy. They are notoriously difficult to solve exactly. In most situations, physicists resort to approximations. Schwarzschild found the exact solution for the simplest possible case: a perfectly spherical, non-rotating, electrically neutral mass sitting in otherwise empty space. The solution was elegant. It described the curvature of space-time around such an object with perfect mathematical precision, and embedded within it was something that nobody quite knew what to make of. At a certain distance from the center of the mass, a radius now known as the Schwarzschild radius, the mathematics behaved strangely. Certain terms in the equations became infinite. The geometry, in a formal sense, broke down. For an object like the Sun, the Schwarzschild radius is tiny, roughly 3 kilometers. The Sun's actual radius is nearly 700,000 kilometers. So the problematic region lies deep inside the solar interior, well hidden. For the Earth, the Schwarzschild radius is even smaller, less than a centimeter. Schwarzschild sent his solution to Einstein from the Eastern Front. Einstein was astonished. He wrote back that he had not expected an exact solution to be possible so soon, and that the result was genuinely surprising. He presented Schwarzschild's paper to the Prussian Academy of Sciences in January of 1916. Karl Schwarzschild died in May of the same year of a disease contracted at the front. He was 42. He never learned what his equations would eventually be understood to describe. For decades after, the singularity in Schwarzschild's solution was treated as a mathematical curiosity, a feature of a perfectly idealized geometry that would disappear if you introduced any of the messiness of real physics. Einstein himself published a paper in 1939 arguing that no real physical process could compress matter enough to reach the Schwarzschild radius. He was, as it turned out, wrong. Oppenheimer and the inevitable collapse. The correction came from an unexpected direction. In 1939, J. Robert Oppenheimer, then a theoretical physicist at Berkeley, not yet the figure he would become as director of the Manhattan Project, published a paper with his graduate student Hartland Snyder that changed the conversation permanently. Oppenheimer and Snyder studied what happens when a very massive star exhausts its nuclear fuel. Stars are, in a sense, held up by their own energy output. The nuclear reactions in a star's core produce an outward pressure that balances the inward pull of gravity. When the fuel runs out, that pressure disappears. What follows depends on the mass of the star. For stars of modest mass, the collapse is halted by quantum mechanical effects, the resistance of electrons or neutrons to being compressed beyond a certain density. These produce white dwarfs and neutron stars, respectively. But Oppenheimer and Snyder showed that for a sufficiently massive star, there is no quantum mechanical process that can halt the collapse. The star's own gravity overwhelms everything. The core collapses inward, past the density of a neutron star, past every known form of matter, and continues. There is nothing to stop it. The mathematics describes a collapse that proceeds past the Schwarzschild radius, a region of space from which, once matter has fallen inside, nothing, no signal, no light, no particle, can return to the outside. Oppenheimer published this result in September of 1939. The same month, Germany invaded Poland. The paper was largely ignored. The world had other things on its mind, and the physics community was also distracted. Many of its members were about to be recruited into weapons programs. The result sat, largely unread, for years. It was not until the 1960s that the subject was revived in earnest, and the full implications of Oppenheimer and Snyder's paper began to be worked through. A name that stuck. The person most responsible for bringing black holes into the mainstream of theoretical physics was the American physicist John Wheeler. Wheeler was not primarily a calculator. He was a conceptual thinker, a person who had a gift for the right word at the right moment, and an unusual willingness, for a physicist of his generation, to embrace the strangest implications of the theories he worked with. In 1967, at a conference in New York, Wheeler used the term black hole in a public lecture. He had not invented the concept. The name had apparently been suggested to him by a member of the audience at an earlier event, but his adoption of it and his habit of using it consistently and publicly caused it to spread rapidly. Before black hole, the objects had been called collapsed stars, frozen stars, dark stars, and various other ungainly names. None of them stuck. Black hole did, not despite its slightly unsettling connotations, but perhaps partly because of them. The name captured something real about the object, a void, a darkness, a hole in the structure of the visible world. Wheeler spent the following years working to understand and describe these objects more completely, and he attracted a generation of brilliant students, including Kip Thorne, who would decades later lead the project that first detected gravitational waves. What a black hole actually is. By the 1970s and 80s, the basic picture of a black hole was well established, at least in theoretical terms. Let's walk through it carefully, because the details matter for everything that follows. A stellar black hole forms when a massive star, typically one with at least 20 to 25 times the mass of our Sun, reaches the end of its nuclear fuel supply. The collapse, when it comes, is extraordinarily rapid. The core falls inward in less than a second. If the core's remaining mass exceeds a threshold of roughly 2 to 3 solar masses, the collapse cannot be halted. It continues past neutron star densities, past any known form of resistance, until the matter reaches, in theory, a singularity, a point of zero volume and infinite density. The singularity is at the center. The event horizon surrounds it at the Schwarzschild radius, and outside the event horizon, the black hole is in most ways simply a very massive object. It exerts gravity on surrounding matter exactly as any other mass would, following Newton's and Einstein's rules. A black hole, the mass of the Sun, would not suddenly start sucking in the solar system. The Earth would continue orbiting in exactly its current path. What changes is what happens if you get close enough to cross the horizon. The event horizon is not a physical surface. There is no wall there, no membrane, no fire. At least not in the standard picture. Though, as we'll discuss later, some physicists have challenged even this. It is a mathematical boundary, a threshold defined by the geometry of space-time. If you were falling toward a black hole in a small spacecraft, you would cross the event horizon without any local physical measurement alerting you. The equations say the crossing would feel, in the moment, completely ordinary. What changes is your future. Once inside the horizon, every path through space-time, every direction you could travel, every future you could reach, curves inexorably toward the singularity. You cannot go back, not because something is blocking you, but because the geometry of space-time itself no longer contains a path that leads outward. From the perspective of someone watching you fall from a safe distance, the picture is different and stranger. As you approach the event horizon, The light you emit takes longer and longer to climb out of the gravity well and reach the observer. Your image appears to slow. The light reaching the observer becomes increasingly redshifted, stretched to longer wavelengths, losing energy. Eventually, your image appears to freeze, dimming and reddening at the horizon, suspended there for as long as the observer cares to watch. You appear never to cross, but you already have, long ago, from your own perspective. This disconnect between the infalling and outside perspectives is one of the most genuinely strange features of black hole physics, and it has no comfortable everyday analogy. It is simply what the mathematics describes, and the mathematics has been tested enough in enough different ways to be taken seriously. The universe's largest black holes, formed from the deaths of individual stars, we now know about a class of objects that operate on an entirely different scale. Supermassive black holes are found at the centers of virtually every large galaxy that has been examined. They range in mass from a few 100,000 solar masses to several tens of billions. The black hole at the center of our own Milky Way, designated Sagittarius A, has a mass of approximately 4 million solar masses. It sits about 26,000 light-years from Earth in the direction of the constellation Sagittarius. For decades, Sagittarius A was inferred from the motion of stars near the galactic center. Stars whose orbits could only be explained by the presence of an enormous, compact mass in a very small region of space. The inference was strong, but a direct image had to wait until 2022, when the Event Horizon Telescope collaboration, the same international network of radio telescopes that had previously imaged the black hole in the galaxy Messier 87, released the first direct picture of our galaxy's central black hole. How supermassive black holes formed is one of the genuinely open questions in modern cosmology. The standard picture of stellar black holes growing over time by accreting surrounding matter doesn't work well for the largest of them. Observations of the very distant, very early universe, looking back to within the first billion years after the Big Bang, have found supermassive black holes already present at enormous masses. There hasn't been enough time in the standard cosmological story for them to have grown that large through ordinary accretion. Several competing explanations have been proposed. The direct collapse of massive early gas clouds, the rapid merging of many smaller black holes, or some process involving the unusual conditions of the early universe that has no present-day equivalent. None of these explanations has been confirmed. This is an active and unresolved area of research. The James Webb Space Telescope, launched in 2021 and operational from 2022 onward, has been providing new observations of early universe black holes that have, in some cases, deepened the puzzle rather than resolved it. Hawking's quiet revolution. One more piece of the foundation before we move into the theories, because in 1974, Stephen Hawking published a paper that quietly changed everything about how physicists understood black holes and opened the deepest unsolved problem in the field. The paper was called Black Hole Explosions? The question mark, a characteristically understated signal that what followed was genuinely surprising. Hawking had been working on the application of quantum mechanics to the region just outside a black hole's event horizon. Quantum mechanics, at its most fundamental level, describes a universe that is never fully at rest, even in apparently empty space. The uncertainty principle permits the momentary appearance and disappearance of particle-antiparticle pairs, a phenomenon called quantum vacuum fluctuations. These pairs appear, briefly exist, and annihilate each other, returning their borrowed energy to the vacuum. Near the event horizon of a black hole, Hawking showed something different can happen. A pair of particles appears near the horizon. One falls inside. The other escapes outward into space. The infalling particle carries negative energy, effectively reducing the black hole's mass. The escaping particle carries positive energy and flies away from the black hole as real radiation. The cumulative effect is that the black hole slowly radiates energy. It loses mass over time. And eventually, over timescales so vast that they make the current age of the universe seem like a heartbeat, it evaporates entirely. This radiation is now called Hawking radiation. It has never been directly observed. For any black hole of astrophysical size, the radiation would be so extraordinarily faint, far fainter than the cosmic microwave background, that detecting it with current technology is essentially impossible. But the theoretical derivation is widely considered sound, and it has been confirmed through multiple independent mathematical approaches. The implications are profound. Black holes are not permanent. They are mortal. They are, in a sense, burning very, very slowly, and the fire will outlast everything else we know. But the deeper implication is the one that Hawking himself wrestled with for the rest of his life. When the black hole is gone, when the last trace of Hawking radiation has dispersed into the cold of an old universe, what has happened to everything that ever fell in? Every star, every planet, every human being who crossed that horizon, every atom, every quantum state, every piece of information encoded in every particle of matter. Quantum mechanics says that information cannot be destroyed. The complete quantum state of a physical system must, in principle, be recoverable. This is not simply a convenient rule. It is a foundational symmetry of the theory, without which quantum mechanics as a whole would cease to be consistent. Hawking radiation, as originally calculated, appears to carry no information about what fell in. It is thermal, random, featureless, the quantum equivalent of static. If a library fell into a black hole and the black hole evaporated into featureless Hawking radiation, the library is gone. Every word, every thought, every pattern erased. This is called the black hole information paradox. It is not a philosophical puzzle. It is a sharp mathematical contradiction between two of our best theories, and it demands resolution. Either quantum mechanics is not quite what we think it is, or general relativity is not quite what we think it is, or both. Something has to give. Hawking initially believed that information was genuinely destroyed, that black holes represented a fundamental exception to quantum mechanical information conservation. He defended this position for decades, and it was deeply controversial. He eventually conceded the point in 2004, betting that information is ultimately preserved, though exactly how remains one of the most actively debated questions in theoretical physics. It is this paradox, this place where two beautiful, well-tested theories look at each other and disagree. That serves as the gateway to everything we're going to look at next. Because when the best physics we have breaks down, that is precisely where the most interesting questions begin. Black holes, as portals or wormholes, the most enduring and romantic theory about black holes, is also, in a sense, the most scientifically adjacent. The claim is this: black holes are not simply dead ends. They are passageways, tunnels through space-time, connecting one region of the universe to another, or connecting our universe to an entirely different universe altogether. This idea did not originate in science fiction, though science fiction has carried it further than physics currently allows. It originated in the same equations that gave us black holes in the first place. And the story of how it got there is worth telling carefully, because it begins with a coincidence of timing that is, in retrospect, one of the more remarkable moments in the history of physics. The year was 1935. Albert Einstein was 56 years old, living in Princeton, New Jersey, having fled Europe as the political situation deteriorated. He was working, as he often did, on the mathematical structures of general relativity, not so much doing new physics as trying to understand the full implications of what he had already built. He was also deeply troubled by quantum mechanics. That year, Einstein co-authored two papers that would decades later, turn out to be secretly about the same thing. The first, written with his assistant Nathan Rosen, examined the internal structure of the Schwarzschild solution, the same geometry that described black holes. Einstein and Rosen found that the mathematics permitted a kind of bridge, a narrow throat connecting two separate regions of space-time, or two separate sheets of the space-time geometry, through a single point. They called it a bridge. We now call it an Einstein-Rosen bridge. The word wormhole came later, coined like black hole by John Wheeler, who had a talent for naming things memorably. The second paper, written with Boris Podolsky and Nathan Rosen, described a peculiar prediction of quantum mechanics. Two particles that have interacted can become entangled, correlated in such a way that measuring one instantly determines something about the other, regardless of how far apart they are. Einstein found this deeply troubling. He called it spooky action at a distance and used the paper, known ever after as the EPR paper, to argue that quantum mechanics must be incomplete. Einstein wrote both papers in the same year. He did not believe they were connected, and for nearly 80 years neither did anyone else. The Einstein-Rosen bridge, in its original form, was not particularly promising as a portal. The mathematics showed the bridge existed, but it was a dynamic structure. It formed and collapsed so rapidly that even light could not traverse it in time. It was, in effect, a passageway that slammed shut before anything could pass through. Einstein and Rosen knew this. They were not proposing wormholes as a travel mechanism. They were exploring the geometry, seeing what the equations contained. Over the following decades, other physicists examined the wormhole geometry more carefully. In 1957, Wheeler and a colleague named Charles Misner developed the concept of what they called geons, structures of space-time topology, and explored the possibility of wormhole-like connections more formally. The word wormhole first appeared in this period. By the 1980s, the question of traversable wormholes had been examined seriously enough to produce a definitive answer of sorts. A physicist named Kip Thorne, who would later win the Nobel Prize for his work on gravitational waves, was approached by the science fiction writer Carl Sagan, who was working on his novel Contact and wanted to know whether wormhole travel was physically plausible. Thorne took the question seriously and worked through the mathematics carefully. The conclusion was this: a traversable wormhole, one through which matter could actually pass, is not forbidden by general relativity. The equations permit it. But maintaining one open would require a form of matter with a property that has never been observed in nature: negative energy density. This hypothetical substance is usually called exotic matter, and its existence, while not strictly ruled out by quantum field theory, has never been confirmed by any experiment. Quantum field theory does predict that certain configurations of quantum fields can produce negative energy in small localized regions. The Casimir effect, measurable between closely spaced conducting plates, is an example of this. But the amounts are extraordinarily small, and whether they could be harnessed or scaled to hold a wormhole open is, by any current understanding, far beyond anything physically achievable. So the traversable wormhole remained theoretical, permitted but not practical. A possibility encoded in the mathematics, waiting for something that could make it real. And then, in 2013, something changed. Not experimentally, but conceptually. Two physicists, Juan Maldacena at the Institute for Advanced Study in Princeton and Leonard Susskind at Stanford, published a paper with a deceptively simple title: Cool Horizons for Entangled Black Holes. Its central proposal has since become known in shorthand as ER equals EPR. The ER refers to Einstein-Rosen bridges, wormholes. The EPR refers to the Einstein-Podolsky-Rosen paper on quantum entanglement. The claim of Maldacena and Susskind was that these two things, wormholes and quantum entanglement, are not merely analogous. They are, in a deep and precise sense, the same phenomenon, viewed from different angles. The argument, in broad outline, works like this. Consider two black holes that are quantum mechanically entangled with each other. Their quantum states correlated in the way that EPR describes. Maldacena had previously shown, in an earlier and extraordinarily influential paper, that certain quantum systems with entanglement between their parts are mathematically equivalent to space-time geometries with wormholes connecting those parts. If that equivalence is real, then entanglement is not merely a correlation between distant particles. It is a geometric connection, a thread of space-time joining them. The implication, extended to its logical conclusion, is radical. The fabric of space-time itself, the geometry of the universe, the structure that gives rise to distance and nearness, and the very concept of here and there, might be stitched together by quantum entanglement. The reason two distant regions of space are connected at all, the reason the universe hangs together as a single coherent geometry rather than disconnected fragments, might ultimately be because the quantum fields threading through it are entangled with each other. In this picture, wormholes are not exotic tunnel-shaped objects that exist in some unusual region of space. They are the microscopic quantum-scale threads out of which space-time is woven. The geometry of the universe is, at its finest grain, a network of entanglement. And black holes, with their extreme concentration of entanglement near the event horizon, are simply places where that underlying structure becomes macroscopic and visible. This idea has been enormously influential. It has shaped a generation of work in quantum gravity, string theory, and quantum information theory. It has not been proven in the sense that a laboratory experiment proves a theory, but it has survived considerable theoretical scrutiny and continues to develop. What it does not do, at least not yet, is open a wormhole anyone could travel through. The connections implied by ER equals EPR are, in their current theoretical form, non-traversable. Information cannot be sent through them in any operationally useful way. They are connections without communication, bridges with no road. In the popular imagination, of course, the portal theory has traveled much further than the physics currently allows. Black holes, as shortcuts across vast interstellar distances, the mechanism that makes faster-than-light travel conceivable in countless science fiction narratives. Black holes as gateways between parallel universes, the exits corresponding to entrances elsewhere in a multiverse. Black holes as structures that some intelligence, sufficiently advanced, might have learned to stabilize and traverse. For many people who hold these ideas seriously, outside of academic physics, the question is less about whether the mathematics permits such things. It does, under certain conditions, and more about whether the full picture of what is physically possible has been publicly disclosed. The classified research argument surfaces regularly in discussions of wormhole physics. The reasoning runs roughly like this. The military and intelligence communities of major governments have historically invested in research at the edges of physics when the potential applications were significant. The Manhattan Project demonstrated that a relatively abstract area of physics could become, in a short time, a world-changing technology. The classified programs that followed in directed energy, in aerospace, in materials science, show a consistent pattern of physics being developed out of public view when its applications are strategically important. If wormhole physics is as consequential as the theoretical work suggests, if the geometry of space-time can, under the right conditions, be manipulated to create traversable connections, then it is at least worth asking whether all the relevant research is in the publicly accessible literature. That is not a question physics can answer. It sits in a different territory entirely, the territory of institutional transparency, and the relationship between scientific research and government secrecy. It is worth noting the question without pretending it has an easy resolution: the information paradox and the holographic universe. We touched on the information paradox in the grounding section, but the full weight of it and the extraordinary ideas it has generated deserves more time. Because the information paradox is not a minor technical puzzle. It is a collision between two of the most successful and well-tested theories in the history of science. And the attempts to resolve it have produced proposals about the nature of reality that are, in their implications, among the most disorienting ideas physics has ever seriously entertained. Let's return to the paradox itself, this time in more detail. Quantum mechanics rests on a principle called unitarity. It says, in formal terms, that the quantum mechanical evolution of a system is always reversible, that the complete information about the quantum state of a system at any one moment is, in principle, sufficient to reconstruct its state at any other moment, past or future. Information is never created and never destroyed. It changes form. It becomes extraordinarily scrambled, but it persists. This is not simply a convenient assumption. Unitarity is built into the mathematical foundations of quantum mechanics in a way that, if violated, causes the theory to produce nonsensical predictions, probabilities that don't add up to 1, physical quantities that become ill-defined. Without unitarity, quantum mechanics breaks down entirely. Now consider what Hawking showed in 1974. A black hole radiates energy through Hawking radiation and slowly loses mass. Eventually, it evaporates completely. The Hawking radiation is, in Hawking's original calculation, perfectly thermal, a featureless glow of random particles, characterized only by a temperature carrying no specific information about what fell into the black hole. If a library, every book ever written, every thought ever recorded, fell into a black hole, and the black hole evaporated into featureless thermal radiation, then the information in those books has vanished. Not scrambled, not hidden, gone, erased from the quantum state of the universe. This violates unitarity, and if unitarity is violated, quantum mechanics is not what we think it is. Hawking initially believed that this was simply true, that black holes genuinely destroy information, that they represent a fundamental exception to quantum mechanical reversibility. He published this position, defended it in debates against other physicists for decades, and only conceded in 2004 that information is probably preserved, though he never fully explained how. The community of physicists who disagreed with Hawking, most notably Leonard Susskind and Gerard Hooft, spent years developing an alternative picture. Their argument was that information must be preserved, that unitarity is too fundamental to abandon, and that therefore something in the standard description of black holes must be wrong or incomplete. The first major alternative proposal was called black hole complementarity. The name refers to Niels Bohr's concept of complementarity in quantum mechanics, the idea that the same physical system can be completely described in two different, mutually exclusive ways, and that both descriptions are valid from their respective perspectives. Applied to black holes, the proposal works like this. From the perspective of an observer falling into a black hole, nothing dramatic happens at the event horizon. The informing observer crosses the boundary smoothly, carries all their information with them into the interior, and eventually meets their end at the singularity. The information went inside. From the perspective of an observer remaining outside the black hole, the picture is different. The infalling observer appears to slow, redden, and freeze at the horizon, and the information appears to be absorbed into the horizon itself, scrambled and eventually re-emitted as subtle correlations in the Hawking radiation. The information stayed outside. Both descriptions are complete and internally consistent. The apparent contradiction, information being in two places simultaneously, is not a real contradiction. because no single observer can verify both pictures. The outside observer can never go inside to check. The inside observer can never send a signal back out. The two perspectives are complementary rather than contradictory, and the no-cloning theorem of quantum mechanics, which forbids the exact duplication of quantum information, is not violated because no one can collect both copies. Black hole complementarity is elegant. It was widely accepted for a period, and then in 2012 it ran into a serious problem. A group of physicists, Ahmed Amhiri, Domomarov, Joseph Polchinski, and James Sully, whose initials gave their paper the nickname AMPS, published an argument showing that black hole complementarity cannot be maintained without violating one of three fundamental principles: the unitarity of quantum mechanics, the equivalence principle of general relativity, or the validity of quantum field theory in low curvature space-time. Their specific conclusion was that if information is truly encoded in the Hawking radiation, and if quantum mechanics is fully valid, then the experience of crossing the event horizon cannot be smooth. Instead, an infalling observer would encounter a wall of extremely high energy radiation right at the horizon, what the AMPS paper called a firewall. The firewall would be lethal. It would violate the equivalence principle. Einstein's foundational claim that the experience of gravity is locally indistinguishable from acceleration, and that an observer in freefall should not encounter anything locally dramatic at the horizon of a large black hole. The firewall paper divided the physics community sharply. Some physicists accepted the conclusion reluctantly as the least bad option. Others argued that it contained hidden assumptions that, if relaxed, would dissolve the paradox. The debate has not been resolved. More than a decade later, physicists continue to disagree about whether firewalls are real, and if not, what prevents them. This is the state of the art. The information paradox remains open. The firewall argument has not been refuted, but neither has it been universally accepted. Something is wrong with our picture, and we do not yet know what. It was in this context, the struggle to understand black hole thermodynamics and information preservation, that the holographic principle emerged. The first hints came from work by Jacob Bekenstein in the early 1970s. Bekenstein noticed something peculiar about the thermodynamics of black holes. The entropy of a black hole, the measure of its disorder, the count of its internal states, is not proportional to its volume, as you might expect for an ordinary object. It is proportional to the area of its event horizon. This is strange. For any ordinary physical system, if you double the size, you roughly double the number of degrees of freedom, and roughly double the entropy. Volume scales with entropy. But for a black hole, it is the two-dimensional surface area that determines the information content, not the three-dimensional interior. Hawking confirmed this relationship and extended it, showing that black holes obey laws closely analogous to the laws of thermodynamics, with the horizon area playing the role of entropy, and the surface gravity playing the role of temperature. Gerard Hooft, a Dutch physicist who had won the Nobel Prize for work on particle physics, took the Bekenstein-Hawking result seriously and drew a striking conclusion. If the information content of a black hole is proportional to its surface area, rather than its volume, then perhaps this is telling us something fundamental about information and space in general. Perhaps any region of space can contain no more information than can be encoded on its surrounding surface. Perhaps the three-dimensional world is, in some deep sense, a projection of a two-dimensional description. Leonard Susskind developed this idea further, named it the holographic principle, and made it the centerpiece of a major research program. The specific mathematical realization of the holographic principle that became most influential is known as the ADS/CFT correspondence, developed by Warren Maldacena in 1997. It is a precise mathematical duality between two different theories, a theory of gravity in a particular type of curved three-dimensional space, and a quantum field theory without gravity living on the two-dimensional boundary of that space. The two theories are mathematically equivalent. Every calculation in one has a precise translation in the other. The three-dimensional bulk with gravity is, in a rigorous technical sense, encoded in the two-dimensional boundary without gravity. This is not an approximation or an analogy, it is an exact mathematical equivalence, and it has been used to make and verify quantitative predictions in both directions. It is one of the most mathematically well-established ideas in theoretical physics of the last 30 years, and one of the most widely cited. The disorienting implication, if taken seriously as a statement about reality, rather than merely as a calculational tool, is this: the experience of living in a three-dimensional world, of reaching out and touching a surface and feeling its depth, of moving through space and perceiving distance. All of this may be a projection. The fundamental description of reality may be two-dimensional, and the third dimension may be, in some sense, emergent, a feature of the projection rather than a feature of the underlying substrate. Our universe is not described by the ADS/CFT correspondence in its specific technical form. Our universe has a different geometry, positive cosmological constant rather than a negative one. Whether an analogous duality holds for our actual universe is an active and unresolved research question. But the possibility that it does, that the holographic principle applies not just to a convenient mathematical toy model, but to the real world we inhabit, has not been dismissed. Some of the most serious physicists working today take it as a genuine possibility. If the universe is holographic, if every cubic centimeter of space you have ever occupied is the projection of information encoded on a surface far away, then black holes are not anomalies within it. They are, perhaps, the most honest objects in it. The places where the projection thins, where the underlying two-dimensional structure becomes visible through the cracks in the three-dimensional surface. The places where, if you knew how to look, you might see the seams. Black holes and the simulation theory. Very close to the holographic universe idea, and frequently entangled with it, is a theory that has moved from philosophical thought experiment to genuine scientific discussion over the last 2 decades: the simulation hypothesis. The claim is this: our universe may not be a fundamental physical reality. It may be a computational process, a simulation running on some substrate we have no direct access to, created by some intelligence or system outside the universe as we know it. This sounds, at first hearing, like science fiction, and it has certainly inspired a great deal of science fiction, but it arrived in its current form not from a novelist or a screenwriter, but from a philosopher at Oxford University. And the argument he made was not mystical, but logical, almost frustratingly so. Nick Bostrom published his simulation argument in 2003 in a paper with the deliberately understated title, "Are You Living in a Computer Simulation?" The paper was published in a peer-reviewed philosophy journal and has since been cited thousands of times across philosophy, physics, and computer science. The argument is a trilemma. Bostrom did not claim that we are living in a simulation. He claimed that at least one of 3 statements must be true, and that all 3 are deeply uncomfortable in different ways. The first possibility: almost all civilizations that reach a level of technological development comparable to our current one go extinct before they develop the computational capacity to run detailed simulations of. Conscious minds. Technological civilizations, in this scenario, are nearly always short-lived. The stars are full of ruins. The second possibility: civilizations that do reach the required computational level almost never choose to run simulations of the kind in question. Simulations with conscious inhabitants who are unaware of their simulated nature. Perhaps it is considered unethical. Perhaps it is simply uninteresting. Perhaps there are other reasons we cannot anticipate. The third possibility. We are almost certainly living in a simulation right now. The reasoning behind the third option runs as follows. If civilizations do survive long enough, and do choose to run such simulations, then the number of simulated conscious minds will vastly exceed the number of biological ones. A single civilization running many detailed simulations of its own history would create far more simulated people than actually existed in the original. If you are a conscious mind, and you have no way of knowing whether you are biological or simulated, then the probability that you are biological is vanishingly small, because the biological minds are outnumbered by orders of magnitude. Bostrom himself has said he does not know which of the three options is true. The argument doesn't tell you, it simply shows that you cannot escape all three simultaneously. The connection to black holes enters through a specific and striking set of observations about how physics behaves at its extremes. In a simulated universe, you would expect the simulation to have limits. Any computational system has a maximum resolution, a finer scale below which it does not distinguish between states, a finest unit of time, a maximum amount of information it can process per unit volume. Beyond these limits, the simulation simply doesn't render. The rules break down not because the underlying reality is strange there, but because the computational substrate has reached its boundary. Now consider what physics actually shows us at its limits. Space and time, at the very smallest scales, the Planck length, approximately 1.6 times 10 to the negative 35 meters, and the Planck time, approximately 5 times 10 to the negative 44 seconds, appear to become fundamentally grainy. Below these scales, the concepts of distance and duration lose their usual meaning. Quantum mechanics and general relativity both break down in different ways, and their combined application produces nonsensical infinities. Physicists generally interpret this as a signal that a better theory, quantum gravity, is needed. But the graininess itself, the existence of a minimum unit, is exactly what you would expect if the universe were running on a discrete computational substrate rather than a continuous mathematical one. Quantum mechanics itself has a deeply digital character. Physical quantities come in discrete units, quanta. Energy is exchanged in packets. Angular momentum comes in integer or half-integer multiples of a fundamental unit. The universe, at its finest observable scale, behaves less like a continuous fluid and more like a grid. This is not proof of simulation. There are physical reasons entirely within the standard framework why quantities might be quantized, but the consistency with the computational picture is, at minimum, worth noting. The observation that physicist James Gates made is, perhaps, the most specific and the hardest to dismiss as coincidence. Gates, a theoretical physicist at the University of Maryland, has spent decades working on supersymmetry, a proposed extension of the standard model of particle physics in which every known particle has a corresponding superpartner. In the mathematical structures that appear in supersymmetric string theory, Gates and his collaborators identified something unexpected. Embedded in the equations were structures called adinkras, graph-theoretic objects that encode the relationships between supersymmetric particles. When Gates examined these structures closely, he found that they were mathematically identical to a class of objects well known in computer science, error-correcting codes. Specifically, they resembled a type of code called doubly even self-dual linear binary error-correcting codes, which are used in digital communications to detect and correct errors in transmitted data. Error-correcting codes are not natural objects, they are engineered. They are specifically designed to protect information against the noise and imperfection that afflicts any real transmission channel. Finding their structure encoded in the fundamental equations of physics is, as Gates acknowledged in a widely viewed lecture, either a remarkable coincidence, or something worth thinking about very carefully. Gates himself has been cautious about drawing strong conclusions. He does not claim to have proven the simulation hypothesis, but he has said publicly that the finding unsettled him and that he does not have a satisfying explanation for why the structure is there. The black hole connection deepens when you examine what happens at the singularity. In a simulated universe, the singularity at the center of a black hole need not be resolved. It need not be replaced by some future theory of quantum gravity with a finite and physically meaningful structure. It could simply be the edge of the computed space, the point where the simulation runs out of rendering, where the program returns an error rather than a result. This reframes the physicist's expectation that quantum gravity will resolve the singularity. That expectation assumes the singularity is a problem with our theories, an artifact of pushing equations beyond their range of validity, to be corrected by better equations. In the simulation framework, the singularity might be a feature rather than a bug. The simulation does not need to know what happens there, because nothing can report back from inside the horizon. The singularity is safely hidden. The computational resource of rendering it is never required. This connects in an interesting way to a principle in physics called cosmic censorship. The conjecture associated with Roger Penrose that singularities are always hidden behind event horizons and can never be observed from outside. If cosmic censorship holds, then the breakdown of physics at singularities never propagates to the observable universe. The simulation in this framing is protected from its own rendering failures by a built-in firewall around every computational boundary. The event horizon in this light takes on a new character. It is not merely a point of no return for matter and light. It is a privacy screen, a boundary that prevents the observable part of the simulation from ever encountering the unrendered part. The simulation hypothesis sits in a peculiar epistemic position. It is, in one sense, impossible to disprove. Any evidence against it could be a feature of the simulation. A perfectly constructed simulation would be indistinguishable from base reality by any internal measurement. This makes it, in the strict Popperian sense, unfalsifiable, which is a serious limitation for a scientific theory. But some researchers have argued that a simulation running on finite computational resources might leave detectable signatures, subtle artifacts of the underlying lattice structure. For instance, appearing in the highest energy cosmic rays. A 2012 paper by physicists at the University of Bonn described a specific search strategy. If the universe is a lattice simulation, the distribution of the highest energy cosmic ray particles might show an alignment with the axes of the underlying grid. The search has not yielded a positive result, but the fact that it can be conceived at all suggests the hypothesis is not entirely beyond the reach of empirical investigation. For now, it sits at the edge, a serious idea held by serious people that cannot be confirmed or refuted, and that connects through the language of information, computation, and the behavior of physics at its limits to black holes in ways that feel too specific to be entirely accidental. Whether they are accidental is, tonight, an open question. Black holes and the Big Bang / one of the more striking proposals in modern cosmology occupying a legitimate, if contested, place in the scientific literature is the idea that our universe was not born from nothing or from some undefined initial condition, but from the collapse of a star in a larger pre-existing universe. Our Big Bang, in this picture, was someone else's black hole. The idea has a certain vertiginous elegance. It takes two of the most extreme phenomena in physics, the birth of a universe and the death of a star, and proposes that they are the same event seen from different sides of an event horizon. The physicist most associated with developing this idea into a rigorous scientific proposal is Lee Smolin, a theoretical physicist who has spent his career working on quantum gravity and the foundations of cosmology. In the early 1990s, Smolin published a theory he called cosmological natural selection, a framework that was, in his own description, an attempt to apply the logic of Darwinian evolution to the universe itself. The argument begins with the observation that sits at the heart of modern cosmology and has never been fully resolved: the fine-tuning problem. The universe we inhabit is governed by a set of physical constants: the strength of gravity, the mass of the electron, the value of the cosmological constant, the ratio of the electromagnetic force to the strong nuclear force, and many others. These constants appear, as far as we can determine, to be simply given. They are not derived from any deeper principle we know of. They are just the numbers the universe happens to have. And those numbers are, by any reasonable calculation, extraordinarily well suited to the existence of complex structures. Stars, planets, chemistry, life. Change the strength of gravity by a small factor, and stars either burn out in millions of years, rather than billions, or never ignite at all. Change the mass of the electron slightly, and atoms don't form stable structures. Change the cosmological constant by even a tiny amount, and the universe either collapses back on itself immediately, or expands so fast that matter never has time to clump together into anything. The standard response to the fine-tuning problem is the anthropic principle. We observe these constants because if they were different, we wouldn't be here to observe anything. This is logically valid, but feels, to many physicists, deeply unsatisfying. It explains our observations without explaining why those particular values exist. Smolin's proposal offers a different kind of answer. The argument runs like this. When a black hole forms, when a massive star collapses past the Schwarzschild radius, the singularity at the center is not, in Smolin's proposal, a true endpoint. It is a transition. On the other side of that singularity, a new region of space-time begins to expand. A new universe, causally disconnected from the parent, hidden behind the event horizon. The Big Bang of a new cosmos. This new universe inherits the physical constants of its parent, the same strengths of forces, the same particle masses, the same cosmological constant, but with small random variations, analogous to the mutations that occur when biological organisms reproduce. The constants are copied with slight imperfections, universes that happen to have constants well suited to forming black holes, constants that allow stars to form, live long enough to go supernova, and collapse into black holes in large numbers will produce many offspring universes. Universes with constants poorly suited to forming black holes will produce fewer. Over cosmological generations, the population of universes will be dominated by those whose constants are optimized for black hole production. And here is the key insight. The physical constants that maximize black hole production turn out to be, in Smolin's analysis, very close to the constants we actually observe in our universe. The fine-tuning is not coincidental. It is the result of selection. Our universe exists in a state that maximizes its reproductive fitness, just as a well-adapted organism occupies a fitness peak in its environment. This is cosmological natural selection. The universe is, in a precise and testable sense, a product of evolution. The theory makes specific predictions which distinguishes it from many cosmological proposals that are impossible to test. Smolin's framework predicts that our universe's physical constants should be near a local maximum for black hole production, that any small change to the constants should result in fewer black holes, not more. This is, in principle, testable. If a physicist were to show that some modification of the constants would produce significantly more black holes, the theory would be in trouble. Some physicists have argued that exactly this is possible, that changes to the quark masses, for instance, might produce universes with more black holes than ours. This would constitute a falsification of cosmological natural selection, and the debate about whether it actually does is ongoing and technical. Smolin himself has continued to refine and defend the theory. He has extended it to include the possibility that the constants vary continuously across the multiverses of daughter universes, producing a landscape of possible physics that is navigated by the same blind process of variation and selection that Darwin described for biological life. The implications of cosmological natural selection, if it is correct, are worth sitting with slowly. Every black hole visible in the night sky, every stellar remnant, every supermassive engine at the center of a galaxy, every intermediate mass object lurking in the dense cores of ancient star clusters is a doorway, not a metaphorical doorway. A physical threshold beyond which a new space-time is expanding, a new universe is cooling. Perhaps new stars are forming, and new chemistries are developing in the dark. We will never see those universes. The event horizon seals them off completely from any observation we could make. But they are, in this framework, as real as our own, born from the same physics, shaped by nearly the same constants, perhaps producing their own black holes, their own daughter universes, their own unending chain of nested cosmoses. Our own universe, in this picture, had a mother, some star, in some parent universe we will never have access to, exhausted its fuel and collapsed. The singularity at the center of that collapse was, from the other side, our Big Bang. The first fraction of a second of our universe's existence was the interior of someone else's black hole, expanding outward into a space-time that was new. We are, in the most literal sense imaginable, the children of a collapse, and our own universe is not simply a stage on which events occur. It is an organism of a kind it was born. It lives, sustaining its stars, cycling its matter, maintaining the conditions for complexity over billions of years. And it reproduces silently and continuously through every black hole that forms within it, through every massive star that exhausts its fuel and falls inward, through every supermassive engine spinning at the center of every galaxy in the observable sky. The universe is not indifferent. It is not arbitrary. It is, if Smolin is right, precisely the kind of universe that makes more universes. It is, in the deepest sense available to physics, fit. Whether fitness implies purpose, whether the chain of cosmological reproduction points towards something, tends towards something, is going somewhere, is a question that cosmological natural selection does not answer. Physics does not answer it. It opens into territory that science has not yet mapped and perhaps cannot. But the question is there, and on a quiet night with the lights off and the world at rest, it is a genuinely beautiful question to hold. Black holes as alien megastructures. Now we move into territory that mainstream physics does not visit, or at least does not visit officially. Some researchers, working at the intersection of cosmology and the search for extraterrestrial intelligence, have proposed that some of what we observe as black holes, or more precisely, some of what we observe in the behavior of matter and energy near certain extremely dense objects, might not be natural phenomena at all. To understand why this idea is taken seriously by anyone with scientific training, it helps to begin not with black holes, but with a thought experiment proposed by a physicist who was, by any measure, one of the most creative scientific minds of the 20th century. Freeman Dyson was a British-American physicist who worked at the Institute for Advanced Study in Princeton for most of his career. He was known for an unusual willingness to follow ideas to their logical conclusions, regardless of how strange they became. And in 1960, he published a short paper in the journal Science that has been quietly influential ever since. The paper asked a deceptively simple question. What would a truly advanced technological civilization look like from the outside? Dyson reasoned that any civilization powered by energy, and all known civilizations will, if it survives long enough, face a fundamental resource constraint. The energy available on a single planet is limited. The energy radiated by that planet's parent star is vastly larger and almost entirely wasted, streaming outward into empty space in every direction, absorbed by nothing. A sufficiently advanced civilization, Dyson proposed, would eventually build structures to capture that wasted energy. Not necessarily a solid shell, the engineering problems with a rigid sphere around a star are formidable. But perhaps a swarm of habitats and collectors, a loosely distributed network surrounding the star and intercepting its light. Such a structure would be, from a distance, nearly invisible in optical wavelengths. It would absorb the star's visible light, but it would radiate infrared energy as waste heat, the inevitable thermodynamic consequence of doing any work with the captured energy. This became known as a Dyson sphere, and the infrared signature it would produce became known as a Dyson signature, a technosignature in the language of SETI research. Something to look for. No confirmed Dyson sphere has ever been found, but several anomalous stars have been examined as candidates. The most famous, KIC 8462852, designated informally as Tabby's star, after the astronomer Tabitha Boyajian, who first drew attention to it, showed an unusual pattern of irregular dimming that briefly generated significant excitement in 2015. Unlike the regular predictable dimming produced by an orbiting planet, Tabby's star dimmed by amounts ranging from less than 1% to more than 20%, at irregular intervals, with no obvious natural explanation. The speculation was swift. A Dyson swarm under construction, perhaps partial coverage, irregular, producing the uneven dimming. The hypothesis made international news. Further observation eventually provided a more prosaic explanation. Dust, in irregular clouds orbiting the star at various distances. The dimming matched the signature of dust absorption, in a way that satisfied most astronomers. The alien megastructure hypothesis was set aside, though not everyone was fully satisfied with the dust explanation, and some researchers noted that dust and engineering are not mutually exclusive. The extension of the Dyson sphere concept to black holes requires imagining a civilization operating at a scale that makes a Dyson sphere look modest. Physicist Nikolai Kardashev proposed in 1964 a scale for measuring civilizational advancement in terms of energy use. A Type 1 civilization uses all the energy available on its planet. A Type 2 uses all the energy of its parent star, the level at which a Dyson sphere becomes relevant. A Type 3 uses all the energy of its galaxy. A civilization capable of engineering structures around a black hole would be operating somewhere between Type 2 and Type 3, exploiting not stellar energy, but the far more concentrated energy available in the vicinity of a collapsed stellar remnant. And a black hole is indeed a remarkable energy source. The most energy efficient process known to physics is not nuclear fusion, which converts roughly 0.7% of mass to energy. It is the accretion of matter onto a rotating black hole, which can convert up to 42% of the rest mass energy of infalling material into usable energy through the friction and heating of the accretion disk and through mechanisms related to the black hole's rotation. For comparison, the most efficient nuclear reactor converts less than 1%. A black hole accretion disk is, in energy terms, roughly 60 times more efficient than nuclear fission. A rotating black hole also possesses a region called the ergosphere, a zone outside the event horizon where the rotation of the black hole drags space-time itself around with it. Through a process described by physicist Roger Penrose in 1971, known as the Penrose process, is theoretically possible to extract rotational energy from the ergosphere by carefully dropping matter in and allowing it to split, with one piece falling past the horizon on a trajectory that reduces the black hole's angular momentum, while the other piece flies out carrying more energy than the original piece brought in. The extracted energy comes from the black hole's rotation. A civilization that mastered the Penrose process would have access to energy budgets measured in fractions of a solar mass converted entirely to usable work. The output would dwarf anything achievable by stellar-level energy capture. In the technosignature research community, the question of whether black hole environments might show signs of engineering has been raised with increasing seriousness over the last decade. The argument is not that the standard astrophysical explanation for any observed phenomenon is wrong. It is that standard astrophysics and deliberate engineering are not always distinguishable from the outside, especially at vast distances, and that we should at least be alert to anomalies that don't fit naturally. The jets of relativistic plasma that shoot from the poles of active galactic nuclei, regions surrounding supermassive black holes actively accreting matter, are among the most energetic phenomena in the observable universe. They extend for millions of light years. They are tightly collimated, which is itself remarkable for a purely natural process. They carry vast amounts of energy in highly structured, apparently organized configurations. The natural explanation: magnetic fields generated by the accretion disk, twisted by the black hole's rotation, launching and collimating the jets, is well developed and broadly accepted. But some researchers in the technosignature field have noted that the jets' regularity, their stability over millions of years, their extraordinary directionality, all properties that would also be consistent with engineered output. A civilization using a black hole as a power source might route its waste energy into exactly such a jet. A directed beam of radiation, perhaps carrying structured information, perhaps simply disposing of excess energy in a direction away from inhabited space. This is speculative in the extreme, but the point that responsible researchers in this field consistently make is a methodological one. We have spent most of human history assuming that what we see in the sky is natural, because we had no reason to assume otherwise. We are now, for the first time, a technological civilization ourselves, and we know that technology produces observable signatures. The question of whether any of what we observe has a technological origin is no longer purely philosophical. It is an empirical question, and empirical questions deserve investigation rather than assumption. The deepest version of the alien megastructure theory moves past energy extraction into something more fundamental. Some researchers have proposed that black holes might be used not merely as power sources, but as information storage and communication systems, and that these uses might be more natural to a sufficiently advanced civilization than energy extraction, because the information theoretic properties of black holes are in some ways more remarkable than their thermodynamic ones. We have already discussed the holographic principle, the idea that the event horizon of a black hole encodes all the information about everything that has ever fallen in at a surface density that represents the maximum possible information storage per unit area in the universe. No other known physical structure approaches this information density. A black hole is, in this sense, the most efficient filing cabinet that physics permits. A civilization that understood this, that understood how to write information into a black hole by controlling what falls in, and how to read it back out through the subtle correlations in the Hawking radiation, would possess a storage medium of extraordinary capacity and, given the black hole's extremely slow evaporation, extraordinary longevity, the timescales of black hole evaporation are almost incomprehensibly long. A black hole of stellar mass would take approximately 10 to the 67th years to evaporate completely, a number that makes the current age of the universe, at roughly 14 billion years, look like a rounding error. A civilization storing information in a black hole would be storing it for longer than any other medium could preserve it. Against the heat death of the universe, a black hole archive would be among the last structures standing. In this framework, what we observe as the distribution of black holes in the universe, their masses, their locations, their clustering patterns, might not be purely the product of stellar evolution and gravitational dynamics. It might reflect, in part, the deliberate placement of archives, a library built to outlast the stars. The night sky in this telling is not empty. It is full of books we cannot yet read. The electric universe and alternative black hole physics, there is a community of researchers, persistent and largely outside mainstream academia, who take a fundamentally different approach. They do not ask what advanced civilizations might do with black holes. They question whether black holes, in the sense that mainstream physics describes them, exist at all. They call their alternative the electric universe. To understand what the electric universe theory proposes, it helps to start with something that is not in dispute. Plasma is the most common state of matter in the observable universe. Plasma is the fourth state of matter, distinct from solid, liquid, and gas, consisting of ionized particles, a mix of free electrons and atomic nuclei, responsive to electromagnetic fields, in ways that neutral gas is not. Stars are plasma. The interstellar medium is plasma. The intergalactic filaments that connect galaxy clusters are plasma. By mass, well over 99% of all visible matter in the universe is in a plasma state. Plasma is not passive. It carries electric currents. It generates and responds to magnetic fields. It forms structures, filaments, sheets, rings, vortices, through electromagnetic interactions, and these structures can be stable over enormous scales and long timescales. The study of plasma behavior in space is a legitimate and well-funded field of astrophysics, and the role of magnetic fields in shaping everything from stellar coronae to galactic jets is fully acknowledged by mainstream science. The electric universe theory begins from this legitimate foundation and draws a far more radical conclusion, that electromagnetism, not gravity, is the dominant organizing force of the universe at every scale, and that the standard cosmological model, dark matter, dark energy, black holes, the Big Bang, is an elaborate theoretical superstructure built to explain observations that would be simply and naturally explained by plasma physics. The intellectual lineage of the electric universe runs through a Swedish physicist named Hannes Alfvén, who won the Nobel Prize in Physics in 1970 for his work on magnetohydrodynamics, the physics of electrically conducting fluids in magnetic fields. Alfvén was a genuine pioneer whose contributions to plasma physics are uncontested. He was also, later in his career, a persistent critic of what he saw as the mainstream's underestimation of electromagnetic effects in cosmology. Alfvén argued that the large-scale structure of the universe, the filamentary web of galaxy clusters and cosmic voids, resembled in important ways the structures produced by plasma in laboratory experiments and in near-Earth space. He believed that cosmic-scale electric currents flowing along these filaments played a role in structuring galaxies and driving astrophysical phenomena that the gravity-centric mainstream model could not adequately describe. After Alfvén's death in 1995, his ideas were developed and extended by a community of researchers, some with academic backgrounds in physics and electrical engineering, others without, into what became the electric universe framework. In this framework, the objects that mainstream physics identifies as black holes are reinterpreted as dense plasma structures, what electric universe researchers call plasmoids or Birkeland current foci. The extraordinary energy output of active galactic nuclei, the jets, the accretion disk radiation, all of it is attributed not to matter falling into an infinitely deep gravitational well, but to the behavior of intense electrical currents pinching and discharging in dense plasma. The visual similarity between laboratory plasma formations and astrophysical structures, is a central piece of evidence for this view. When electric currents flow through plasma, they tend to form filaments that attract each other and wind around each other, a phenomenon called the pinch effect. At sufficiently high current densities, these filaments can produce extremely energetic discharges that closely resemble, in shape and behavior, the jets and lobes observed around active galactic nuclei. The mainstream response to the electric universe is not simply dismissal, though the framework is not accepted. It engages with specific claims and finds them wanting in specific ways. The gravitational wave detections by LIGO are the sharpest challenge. The waveforms produced by black hole mergers match the predictions of general relativity with extraordinary precision. The specific frequency, the rate of chirp, the ring down after merger, these are not qualitative matches. They are quantitative predictions, precise to many decimal places, confirmed across dozens of events. The electric universe framework does not make equivalent predictions for these events, and its proponents have not offered a detailed account of what their model predicts for gravitational wave signals. The Event Horizon Telescope image of Messier 87's central black hole presents a similar challenge. The image shows a ring of emission with a specific brightness asymmetry, brighter on one side, because the emitting material is moving toward us on that side, boosting the signal through Doppler effects, surrounding a darker region whose size precisely matches the prediction of general relativity for a black hole of that mass. Electric universe proponents argued that the image is consistent with a dense plasma torus, but they did not produce a prior prediction of the image's specific properties that could have been confirmed or refuted. This is a methodological point that goes to the heart of what science does. A theory that can explain observations after the fact in several different ways without making prior predictions is not as strong as a theory that makes specific, precise, surprising predictions and then sees them confirmed. That said, the electric universe raises a genuine epistemological question that is worth carrying with you, even if you set the specific theory aside. How much of what we believe about the cosmos is directly observed, and how much is inferred through the lens of a theoretical framework that we have already committed to? The black hole at the center of our galaxy was not observed directly for decades. Its existence was inferred from the orbits of nearby stars. The inference is strong, extraordinarily strong, but it is an inference. The image that confirmed it is an image of radio waves, processed through an algorithm, interpreted through a model. The black hole itself has never been touched, tasted, heard, or directly perceived by any human instrument. This is not a criticism. It is simply the nature of cosmology. We are finite beings on a small planet using light and mathematics to reason about objects at distances our intuition cannot compass. The inferential chain is long, and it is carefully maintained, and it is the best we have. The electric universe, at its best, is a reminder to hold that chain lightly, to remember that the map is not the territory, and that the universe is under no obligation to match our most elegant equations. Whether it does or doesn't, in this instance, the answer points back to the same place all the other threads have pointed tonight, to the edge of what we know and the open dark beyond it, black holes and consciousness. This is where things get very strange and very quiet. Up to this point, we've been moving through ideas that, even when speculative, remain grounded in physics, as it is usually practiced, equations, observations, competing interpretations of measurable phenomena. But here, the direction shifts slightly inward. The question is no longer just about what black holes are, but about what experience itself might be, and whether the two are connected at a level deeper than either physics or neuroscience has yet fully explained. There is a small but serious tradition of researchers who propose a connection between black holes, or more precisely, between the physics of extreme gravity and quantum information. and the phenomenon of consciousness. The most prominent version of this idea comes from physicist Roger Penrose and anesthesiologist Stuart Hameroff, who developed a theory called orchestrated objective reduction, or ORC or OR, beginning in the 1990s. To understand what they were proposing, it helps to begin with something Penrose had been thinking about for many years before ORCH, OR, took its final form. Penrose was interested in a very specific question: is human consciousness computable? In other words, could everything that happens in the human mind, every thought, every perception, every moment of awareness, be simulated by a sufficiently advanced computer running the right algorithm? Or is there something about consciousness that cannot be reduced to computation, something that escapes the logic of step-by-step processing? Most researchers in artificial intelligence and neuroscience lean toward the first view. The brain, in this framework, is a biological computer. Neurons fire, signals propagate, patterns emerge. Consciousness is what it feels like when enough complexity accumulates. Penrose disagreed. Drawing in part on mathematical arguments related to Gödel's incompleteness theorems, he suggested that human understanding, especially mathematical insight, involves something that cannot be captured by any algorithm. There is, in his view, a non-computable element in conscious thought. If that is true, then consciousness cannot be fully explained by classical physics, which is, at its core, computational. Something else must be involved. Penrose proposed that this something else lies in quantum mechanics, specifically in the process by which quantum possibilities become definite outcomes. In standard quantum mechanics, systems exist in superpositions, combinations of multiple possible states, until they are measured or otherwise interact with the environment in a way that forces a single outcome. This transition is called wave function collapse, and it is one of the most mysterious aspects of the theory. Penrose proposed that wave function collapse is not merely a feature of measurement or observation. It is a real physical process, one that occurs when quantum superpositions become unstable due to gravitational effects. His idea, called objective reduction, suggests that when a quantum system involves different possible space-time geometries, different ways of curving space-time, there is a threshold beyond which the superposition cannot be maintained. At that point, the system chooses a definite state, collapsing in a way that is not random but influenced by the underlying geometry of space-time. This is where black holes enter the picture. The singularity at the center of a black hole represents the ultimate breakdown of space-time geometry. It is where general relativity reaches its limits, where curvature becomes infinite, where the structure of space-time itself can no longer be described by our current theories. Penrose suggested that the same physics, the same interface between quantum mechanics and space-time geometry is at work, in a much subtler way, in the brain. Stuart Hameroff brought a biological mechanism into the picture. Inside neurons are structures called microtubules, cylindrical protein filaments that help maintain the cell's shape and play a role in intracellular transport. Hameroff proposed that microtubules might also support quantum processes, that they could sustain coherent quantum states long enough to influence neural activity. In the ORCH-OR model, quantum superpositions occur within microtubules. These superpositions evolve according to quantum rules, exploring multiple possible states simultaneously. When they reach a threshold determined by Penrose's objective reduction criterion, tied in this theory to quantum gravity, they collapse into a definite state. Each such collapse corresponds to a moment of conscious awareness. The orchestrated part of ORC-OR refers to the idea that these quantum processes are not random or isolated. They are influenced, orchestrated by the structure and activity of the brain. integrating quantum events into the larger neural network. In this framework, consciousness is not produced by the brain in the way heat is produced by a fire. It is a process that involves the deepest level of physical reality, a bridge between quantum mechanics and gravity, expressed in biological form. This theory has been controversial from the beginning. The most common objection is straightforward. The brain is warm. It is wet. It is noisy. Quantum coherence. The delicate state required for superpositions to persist is typically destroyed very quickly in such environments through interactions with surrounding molecules. This process, called decoherence, is one of the reasons quantum effects are usually only observable in highly controlled laboratory conditions. Mainstream neuroscience argues that any quantum coherence in the brain would decohere far too quickly to play a meaningful role in cognition. The timescales are simply too short. Hameroff and his collaborators have responded by pointing to evidence that quantum effects can and do occur in biological systems. Photosynthesis, for example, appears to involve quantum coherence in the transfer of energy within plant cells. Certain birds are thought to navigate using quantum effects in their visual systems. Enzymes may exploit quantum tunneling to accelerate chemical reactions. These examples do not prove that the brain uses quantum computation, but they show that biology is not entirely classical. Under the right conditions, quantum processes can be sustained and harnessed. Whether microtubules provide those conditions remains an open question. What makes the Wormhole theory particularly relevant to black holes is not just the shared involvement of quantum gravity, but the deeper suggestion it carries. If Penrose is correct, then the collapse of quantum superpositions, the transition from possibility to actuality, is tied to the structure of space-time itself. Consciousness, in this view, is not an emergent property of matter alone. It is a feature of the relationship between matter and space-time. The singularity at the center of a black hole represents the most extreme expression of that relationship. It is where space-time itself becomes unstable, where the usual distinctions between space and time, inside and outside, before and after, begin to dissolve. Consciousness in the Wormhole framework is a much gentler version of the same phenomenon, a localized, low-energy interface between quantum states and space-time geometry, a place where the universe, in a very small way, resolves its own possibilities into actual experience. This leads to a quiet, almost poetic question. If consciousness arises from the same underlying physics that governs black holes, if both involve the collapse of quantum possibilities into definite realities, then what is the relationship between them? What is it like, in principle, to be at the center of a black hole? And what is it like, in principle, to be conscious? These questions are not the same, but in this framework, they are not entirely unrelated either. It is important to be clear about the status of this idea. It is not established science. It is not widely accepted. It remains speculative, and many researchers consider it unlikely. The evidence for quantum computation in the brain is incomplete. The theory of objective reduction has not been experimentally confirmed, and yet it persists. It persists because it attempts to address something that neither physics nor neuroscience has fully explained. Why there is subjective experience at all. Why there is something it feels like to be here. Black holes raise a similar kind of question. In a different domain, they show us that our theories of the physical world are incomplete, that there are places where the equations stop, where the map ends, where we do not know what lies beyond. The connection between the two may be real. It may not be. But the fact that serious researchers have drawn the line between them is in itself worth noticing, because it suggests that the boundary between the inner and the outer, between consciousness and cosmos, may not be as absolute as it appears. The black hole at the center of everything. There is a final direction worth walking through, slowly, before we move toward the counterpoints. It is not a single theory so much as a cluster of related intuitions, ideas that appear in different forms in the work of different researchers, often at the edges of mainstream physics. The suggestion is this: black holes are not just one kind of object among many. They are, in some sense, fundamental. The universe is organized around them more deeply than we currently understand. The starting point for this idea is not speculative. It is observational. Every large galaxy we have studied appears to contain a supermassive black hole at its center. This is not a rare feature. It is, as far as current data suggests, a universal one. And more than that, there is a striking relationship between the properties of these central black holes and the galaxies that surround them. This relationship is known as the M-sigma relation. In simple terms, it states that the mass of a galaxy's central black hole is closely correlated with the velocity dispersion of stars in the galaxy's bulge, a measure of how fast stars are moving within it. The correlation is tight. If you know the velocity dispersion, you can predict the black hole's mass with surprising accuracy. There are other correlations as well. The mass of the black hole relates to the total mass of the galaxy's central region. It relates to the rate at which the galaxy forms new stars. It appears to be connected in a deep and systematic way to the structure and evolution of the galaxy as a whole. This is not what you would necessarily expect if black holes were merely passive objects sitting at the centers of galaxies. The mainstream explanation for these correlations is called coevolution. In this picture, galaxies and their central black holes grow together over time. Gas falls into the galaxy, forming stars. Some of that gas also falls toward the center, feeding the black hole. As the black hole accretes matter, it releases energy in the form of radiation and jets that can heat or expel gas from the surrounding region, regulating the rate of star formation. This creates a feedback loop. The black hole influences the galaxy, and the galaxy influences the black hole. Over billions of years, this mutual interaction produces the observed correlations. This explanation is widely accepted. It is supported by simulations and observations, but it is not complete. The details of how the feedback works, how it remains stable over such long timescales, how the initial conditions are set, these are still areas of active research. The fringe extension of this idea takes a step further. It suggests that black holes are not merely participants in the evolution of galaxies, they are the organizing principle. In this view, galaxies form around black holes, rather than black holes forming within galaxies. The central black hole is not a byproduct of galactic evolution, it is the seed. Some versions of this idea propose that primordial black holes, formed in the early universe, acted as gravitational anchors around which matter accumulated, eventually forming galaxies. Others suggest that the process is more dynamic, that black holes and galaxies emerge together from deeper structures we do not yet fully understand. There is, at present, no strong evidence that black holes precede galaxies in this way. But the question remains open because the early universe is difficult to observe directly, and the formation of the first galaxies is still not fully understood. From here, the idea begins to take on a more philosophical tone. If black holes are central to the structure of galaxies, and galaxies are the fundamental building blocks of the large-scale universe, then black holes may play a role in organizing the cosmos at every level. Some researchers have drawn analogies between black holes and nodes in a network, points where information is processed, transformed, and redistributed. The jets emitted by active galactic nuclei carry energy and matter across vast distances, influencing the formation of stars and the distribution of gas. In this sense, black holes are not just sinks, they are engines. The analogy has been extended further. In biological systems, complex behavior emerges from networks of interacting components, cells, neurons, organs, each performing local functions while contributing to a global pattern. Feedback, regulation, adaptation, these are the hallmarks of life. Some have asked whether the universe at its largest scales might exhibit similar properties, not life in the biological sense, but something analogous, a system that processes information, that evolves, that maintains structure over time through feedback and interaction. In this analogy, black holes are not just objects. They are functional units, the places where the most extreme transformations occur, where information is compressed, where energy is redistributed, where new structures may emerge. This is, by any conventional measure, speculation, but it is speculation that arises from real observations and real gaps in our understanding. Why do supermassive black holes exist at all, so early in the universe's history? How did they grow so large so quickly? Why are their properties so tightly correlated with the galaxies that contain them? Why does the universe have the structure it does? A web of filaments and clusters with vast voids between, and not some other structure. These are not fringe questions. They are central to modern cosmology. The answers, for now, remain open. And in that openness, there is space, quiet space, for ideas that stretch a little further than the data, but not so far that they lose contact with it. Black holes, in this sense, are not just mysteries to be solved. They are anchors, points in the map where the known world meets the unknown, and where the lines we draw to understand it begin to blur, soften, and eventually disappear into something deeper. Of course, not everyone finds these theories convincing, and it is worth taking some time here not to dismiss what we have explored, but to place it gently against what the broader scientific community actually believes. And why? Because the story of black holes is not just a story of mystery, it is also a story of extraordinary success. One of the clearest examples we have of human beings using mathematics to describe something real far beyond direct experience, and getting it right. So before we drift too far into speculation, it helps to return to the ground. The strength of the evidence. The first and most important counterpoint is about the strength of the evidence for black holes themselves. For many decades, black holes were theoretical objects. Elegant, unsettling, but not directly observed. That is no longer the case. In April of 2019, the Event Horizon Telescope collaboration released the first image of a black hole, the supermassive object at the center of the galaxy Messier 87. It appeared as a glowing ring of light surrounding a dark central region, exactly as general relativity predicted. The shape of that ring was not arbitrary. Its size matched the expected diameter of the event horizon for a black hole of that mass. Its brightness was uneven, brighter on one side than the other, precisely as expected from relativistic effects, matter moving toward us appearing brighter due to Doppler boosting, matter moving away appearing dimmer. This was not a vague resemblance. It was a detailed match between prediction and observation. 3 years later, in 2022, the same collaboration released an image of Sagittarius A, the black hole at the center of our own galaxy. This was a more difficult target. Smaller, more variable, but the result again matched the theoretical predictions. These images do not prove that general relativity is the final complete theory of gravity, but they do confirm that objects behaving exactly like black holes, with event horizons, with light-bending geometry, with the specific space-time structure predicted by Einstein's equations, exist in the universe, listening to collisions. The second major line of evidence comes not from light, but from sound, or something very close to it. In 2015, the LIGO Observatory in the United States detected gravitational waves for the first time. These are ripples in space-time itself, predicted by general relativity a century earlier. The signal they detected came from the merger of two black holes, more than 1 billion light-years away. As the black holes spiraled toward each other, they emitted gravitational waves whose frequency and amplitude increased in a characteristic pattern. A chirp, as they approached, merged, and settled into a single, larger black hole. The remarkable thing is not just that the signal was detected, it is that the signal matched almost perfectly the predictions made by solving Einstein's equations for such a merger. The frequency curve, the amplitude, the final ring down, the way the newly formed black hole settled into a stable state, all of it aligned with theoretical models developed years in advance. Since that first detection, dozens more have followed. Black hole mergers of different masses, different spins, different distances, all producing signals that match the predictions of general relativity. This is a level of confirmation that is difficult to overstate. It means that black holes are not just plausible. They behave under extreme conditions, exactly as the theory says they should. Why this matters for alternatives? This matters when evaluating alternative frameworks like the electric universe. Because the scientific theory is not judged only by whether it can explain what we already see. It is judged by whether it can predict what we have not yet seen, and then match those predictions when new observations arrive. General relativity predicted gravitational waves. It predicted their form. It predicted how black holes would merge. And when the instruments became sensitive enough, those predictions were confirmed. Any alternative theory, whether based on plasma physics, electromagnetic structures, or something else, would need to reproduce these predictions with equal precision. Not approximate them, match them. So far, no alternative framework has done so. This does not mean alternatives are impossible. It means the bar they must clear is very high. And that bar has been set by a theory that has now passed some of the most demanding tests we have ever devised, the limits of speculation. The second counterpoint concerns the more abstract ideas, the holographic universe, the simulation hypothesis, the deeper interpretations of the information paradox. These ideas are intellectually serious. They are explored by respected physicists, but they share a common feature. They are extraordinarily difficult to test. Take the holographic principle. In its precise mathematical form, the ADS/CFT correspondence, it is well established. It works beautifully in a specific type of space-time with negative curvature. But our universe does not have that geometry. Extending the principle to our universe is an open problem, and it is not yet clear whether it can be done. The idea that our universe is literally a hologram, that three-dimensional reality is a projection from a two-dimensional boundary, is therefore not confirmed. It is a possibility suggested by mathematical analogies, not an established fact. The simulation hypothesis faces an even deeper challenge. A perfect simulation, by definition, is indistinguishable from reality. Any observation we make could be part of the simulation. Any apparent evidence against it could be simulated as well. This makes the hypothesis extremely difficult to test in a conventional scientific sense. It is not that it is false. It is that it does not, at present, produce clear predictions that could distinguish it from the alternative. Some researchers have proposed possible tests, looking for discrete structure at the smallest scales, searching for anomalies in high-energy physics, but none have produced definitive results. So, the simulation hypothesis remains in a peculiar position, logically possible, philosophically interesting, scientifically ambiguous, the silence of the sky. The third counterpoint applies to the alien megastructure theories. If black holes are being engineered, if galaxies are part of some vast infrastructure, if advanced civilizations are manipulating energy at cosmic scales, then where is the evidence? This is a version of the Fermi paradox, extended to astrophysics. We have observed millions of galaxies. We have mapped the cosmic microwave background. We have catalogued exoplanets, measured stellar spectra, tracked the evolution of galaxies across billions of years, And in all of this data, we have not found unambiguous evidence of artificial structures. There have been anomalies. Tabby's star is one example. Fast radio bursts, before they were better understood, were another. But in each case, further observation has produced natural explanations that fit the data more simply. This does not prove that no advanced civilizations exist. The universe is vast, and our observations are limited. But it does suggest that if such civilizations exist, they are either extremely rare or extremely subtle, or operating in ways that do not leave obvious signatures. The baseline assumption of astrophysics, that what we observe is natural, is not a dogma. It is a working hypothesis that has, so far, been consistently successful. The brain and the quantum. The fourth counterpoint concerns the connection between black holes and consciousness. The Wormhole theory is imaginative and ambitious. It attempts to bridge two of the deepest mysteries in science, quantum gravity and conscious experience. But it faces significant challenges. The most immediate is the problem of decoherence. Quantum states are fragile. They are easily disrupted by interactions with the environment. In laboratory conditions, maintaining quantum coherence requires extreme isolation, low temperatures, minimal interference. The brain is the opposite of that. It is warm, dynamic, chemically active. Signals are constantly firing. Molecules are constantly colliding. Mainstream neuroscience argues that any quantum coherence in such an environment would collapse almost instantly, far too quickly to play a role in cognition. There is ongoing research into quantum effects in biology, and some evidence suggests that certain biological systems can sustain coherence under specific conditions. But extending this to the complex, large-scale processes of the brain remains speculative. Meanwhile, neurocircuits continues to make progress using classical models, mapping neural circuits, understanding how patterns of activity correlate with perception and behavior, developing increasingly detailed models of brain function. This does not solve the hard problem of consciousness, why subjective experience exists at all. But it does suggest that much of what the brain does can be explained without invoking quantum gravity, the information paradox. Carefully, the fifth counterpoint returns us to the black hole information paradox. It is tempting to treat the paradox as evidence for dramatic conclusions, that reality is fundamentally holographic or simulated, or that black holes are portals to other universes. But the paradox itself does not require any of those conclusions. What it requires is a reconciliation between general relativity and quantum mechanics. This is a known problem. It is one of the central goals of modern theoretical physics. And there are multiple candidate frameworks, string theory, loop quantum gravity, others that attempt to address it. The fact that we do not yet have a complete solution does not mean that the solution will be exotic in the ways we imagine. It may be, but it may also be something more subtle, a refinement of existing theories, a deeper understanding of how information is encoded and preserved. The honest position of mainstream physics is cautious. Information is almost certainly conserved. Quantum mechanics is too well tested to abandon easily. There are promising ideas, holography, complementarity, quantum error correction, that suggest ways the paradox might be resolved. But there is no consensus yet, no final answer. And that uncertainty, while frustrating, is not unusual. It is how science moves forward, where this leaves us. So where does all of this leave us? In a place that is, in its own way, quite balanced. On one side, we have a theory, general relativity, that has passed some of the most demanding tests ever devised. We have observations, images, gravitational waves, stellar orbits, that confirm the existence and behavior of black holes with remarkable precision. On the other side, we have questions that remain open. What happens at the singularity? How is information preserved? How do black holes connect to the deeper structure of space-time? Are there aspects of reality, quantum, informational, perhaps even experiential, that we have not yet fully understood? The speculative theories we have explored, wormholes, holography, simulation, cosmic reproduction, alien engineering, consciousness connections, are attempts to answer those questions. Some are grounded in established mathematics. Some are more imaginative. All of them reflect the same underlying fact that black holes sit at the edge of what we know. The important thing is not to accept or reject these ideas too quickly. It is to hold them at the right distance, close enough to see what they are trying to explain, far enough to remember what is actually known. Because the story of black holes is not a finished story. It is a boundary, a place where knowledge ends and curiosity begins. And those boundaries, quiet, uncertain, open, are where some of the most interesting thinking happens. Not because they provide answers, but because they remind us how much there is left to understand. Black holes are, perhaps, the places in the universe where our knowledge most honestly confronts its own edges. Not because we know nothing about them. In fact, we know a great deal. We can predict how they bend light. We can measure how they merge. We can even take images of their shadows from millions of light years away. But what makes black holes different from almost everything else we study is this. The closer we get to understanding them completely, the more clearly we begin to see where our understanding ends. They are not just objects. They are boundaries. So for a little while, instead of trying to resolve everything, we can simply sit with the questions that remain, the ones that physics has not yet answered, and may not answer for some time. What happens at the singularity? The first open question is the simplest to state and the hardest to answer. What actually happens at the singularity? According to general relativity, the singularity is a point of infinite density. Space is compressed to zero volume. Curvature becomes infinite. Time, in a sense, ends. But most physicists do not believe this is literally true. Instead, the singularity is understood as a signal, a warning from the mathematics that the theory has been pushed beyond the range where it applies. General relativity is a classical theory. It does not include quantum effects. And at the extreme densities and energies near a singularity, quantum effects cannot be ignored. Something else must take over. That something else is what physicists call quantum gravity, a theory that would unify general relativity with quantum mechanics into a single, coherent framework. We do not yet have that theory. There are candidates. String theory proposes that the fundamental constituents of reality are not point particles but tiny vibrating strings, whose different modes of vibration correspond to different particles. In this framework, the singularity may be replaced by a complex extended structure, something finite, something that spreads out rather than collapsing to a point. Loop quantum gravity takes a different approach. It suggests that space itself is quantized, made of discrete units, like atoms of geometry. In some models, when matter collapses to extreme density, these quantum properties of space generate a kind of repulsive force, preventing true infinite compression. Instead of a singularity, you get a bounce, a transition from collapse to expansion. In that picture, the interior of a black hole does not end in a point. It opens into something else. Perhaps another region of space-time. Perhaps another universe. But we do not know. We have the equations. We have the frameworks. What we do not yet have is confirmation. No observation, no experiment that can tell us which, if either, of these ideas is correct. So the center of a black hole remains, quite literally, undefined. Is the universe a hologram? The second open question moves outward from the center of a black hole to the structure of reality itself. Is the universe actually a hologram? The holographic principle suggests that everything we experience as three-dimensional space could, in some deep sense, be encoded on a two-dimensional surface. That volume is not fundamental. That depth is perhaps emergent. This idea arises from black hole physics, from the observation that the information content of a black hole scales with its surface area, not its volume. But extending that idea to the entire universe is not straightforward. The most precise version of the holographic principle, the ADS/CFT correspondence, works beautifully in a specific kind of space-time that is not our own. Our universe appears to be expanding at an accelerating rate, with a positive cosmological constant. The mathematics of holography in such a space is still being worked out. And even if the principle does apply, there is a deeper question. What does it mean to live in a holographic universe? If every point in space is, in some sense, a projection of information encoded elsewhere, then what is elsewhere? Where is the boundary? Is it physical? Is it accessible? Or is it something entirely beyond the concepts of space and time as we understand them? These are not questions with clear answers. They are questions that begin to blur the line between physics and philosophy, between describing the universe and interpreting what that description means. What is dark matter? The third open question is more concrete, but no less mysterious. What is dark matter? When astronomers observe galaxies, they find that the visible matter, stars, gas, dust, is not enough to explain how those galaxies behave. Stars at the edges of galaxies orbit much faster than they should, given the amount of visible mass. Light from distant objects is bent more strongly than expected as it passes through galaxy clusters. The simplest explanation is that there is additional mass present, mass that does not emit or absorb light. Dark matter. By current estimates, about 85% of the matter in the universe is dark. It is not a small correction. It is the dominant component, and we do not know what it is. Many candidates have been proposed. Weakly interacting massive particles, axions, other exotic particles that have not yet been detected. But there is another possibility, primordial black holes. These would be black holes formed not from collapsing stars, but from density fluctuations in the very early universe. Tiny regions where matter was slightly more concentrated, collapsing under their own gravity before stars even existed. If enough of these black holes formed, and if they exist in the right mass range, they could account for some or all of the dark matter. This idea is not fringe. It is actively studied. The recent detection of black hole mergers by LIGO has made it more interesting, because some of the observed black holes have masses that are difficult to explain through standard stellar evolution alone. But again, we do not know. Dark matter remains invisible. It reveals itself only through gravity, and gravity, while powerful, does not tell us everything about what it is acting on. Are black holes nearby? The fourth open question brings things closer to home. Are there black holes much nearer to us than we think? The nearest known stellar black holes are hundreds of light years away, close in cosmic terms, but still far beyond any direct interaction. But there is ongoing research into the possibility that much smaller black holes, primordial ones, might exist within our own solar system. One candidate that has drawn attention is the hypothetical Planet 9. Astronomers have observed that certain objects in the outer solar system beyond Neptune have unusual clustered orbits. One explanation is that there is a large unseen planet influencing them. Another, more unusual possibility is that the object is not a planet at all, but a primordial black hole. Such a black hole would be incredibly small, perhaps the size of a grapefruit, but with the mass of several Earths, it would not emit light. It would be detectable only through its gravitational effects and possibly through faint radiation from interactions with surrounding matter. Searches are ongoing. Whether Planet 9 exists, and what it is if it does, remains uncertain. But the possibility itself is a reminder of something easy to forget. Black holes are not only distant, exotic objects at the centers of galaxies, they may be, in some cases, quiet neighbors. Why did the universe begin this way? The fifth open question is perhaps the deepest. Why does anything escape the Big Bang at all? According to the standard model of cosmology, the universe began in an extremely hot, dense state, expanding outward from what is often described as a singularity. But this raises a subtle issue. A singularity, by definition, is a point from which nothing can escape, just like the center of a black hole. And yet, in the case of the Big Bang, everything escapes. Space itself expands. Matter spreads outward. Light travels freely. Why is this singularity different? The answer, at present, is that we do not fully understand the Big Bang. Just as with black hole singularities, general relativity breaks down at the earliest moments of the universe. Quantum gravity must take over. And until we have a complete theory of quantum gravity, the true nature of the Big Bang remains unknown. This is where the connection to black holes becomes particularly interesting. If the interior of a black hole can give rise to a new expanding region of space-time, if collapse can lead to expansion, then the Big Bang may not have been a beginning in the absolute sense. It may have been a transition, a continuation, the interior of something else, a quiet thought. If that is true, and it is only a possibility, then the light we see around us is not the beginning of existence. It is the continuation of a story that began elsewhere. The stars, the galaxies, the faint background radiation filling the universe, all of it could be the afterglow of an event that took place inside a black hole in another universe. A universe we will never see. A universe whose existence we can only infer indirectly through the structure of our own. We are perhaps the interior of something. And just as we cannot see beyond our own cosmic horizon, whatever lies beyond ours cannot see into us. These are not answers. They are not even, in many cases, testable hypotheses. They are the edges of thought, places where the questions become larger than the frameworks we use to ask them. And in the quiet, especially in the quiet before sleep, there is something calming about that. Not knowing is not a failure. It is a boundary. And boundaries in science are not walls. They are invitations. Tonight, we traveled a long way. We began with a university professor in the middle of a world war, scribbling equations at the front. Ink on paper, quiet thought in a noisy world. And from those equations, something unexpected emerged. Not just a solution, but a doorway into a kind of darkness that was not empty, but structured, precise, and strangely inevitable. We followed those equations to their conclusion, a region of space from which nothing returns, a boundary where time becomes something softer, something less certain, something that stretches and bends and eventually slips out of the shapes we're used to holding it in. We paused at the edge of that boundary, and then we moved outward. We visited the first image of a black hole, that faint glowing ring surrounding something darker than darkness, a shadow 55 million light years away, captured by instruments spread across an entire planet, working together like a single patient eye. A quiet achievement, not dramatic, not loud, just a soft confirmation that something we once imagined is really there, still there, waiting. We moved through the ideas that gather around these objects, the ones that stay close to the mathematics, and the ones that wander further out. We walked through the possibility that black holes are not endings, but passages. That space-time itself might fold, connect, and twist in ways that allow distant regions or entirely separate universes to touch briefly in ways we don't yet fully understand. We spent time with the idea that space itself might not be what it seems. That depth, distance, the sense of being here instead of there, all of it might emerge from something simpler, flatter, encoded somewhere we cannot directly see. A surface, perhaps, holding the story of a volume. We stepped into the possibility that black holes are not just destroyers, but creators. That each collapse might be the beginning of something else. That somewhere beyond the reach of any signal, a new expansion might be unfolding. Quiet, invisible, complete. A new sky, a new set of stars. We went deeper still, into the places where the structure of physics becomes less certain. We considered the idea that the universe itself might be something like a simulation, not in a dramatic or artificial sense, but in a quiet, structural way. A system with limits, with resolution, with boundaries that only reveal themselves at the edges, inside black holes, at the smallest scales, in the places where the equations hesitate. We touched on the thought that consciousness, the simple fact of being aware, right now, might not be separate from these questions. That the same physics that governs the most extreme objects in the universe might also be present, in a much gentler form, in the quiet workings of the mind. Not proven, not resolved, but present as a possibility. And we looked outward again at the larger structure of the cosmos, at galaxies and the black holes that sit quietly at their centers, at the strange, consistent relationships between them, at the suggestion, faint but persistent, that these objects are not just parts of the universe, but part of how it organizes itself. And then, slowly, we let all of that settle, because at the end of all these paths, we arrived in the same place, a place of questions. Simple ones when you say them out loud. What is at the center? What is most of the universe made of? Where did all of this come from, really? And perhaps the quietest one. These are not frightening questions. They can feel that way sometimes in bright light, in busy hours, when the mind is looking for firm answers and clear edges. But here, now, in the quieter part of the day, they feel different. They feel open, spacious, almost gentle. They are not demands for answers. They are invitations to wonder. Black holes, in this sense, are not just objects in space. They are reminders that even in a universe we have mapped so carefully, there are still places where the map ends, places where the lines fade and the labels stop, and the territory continues without us. They are the points where understanding slows down, softens, and becomes something else. Something quieter. You've spent this evening near that edge. You've followed the ideas as far as they comfortably go. And now you can let them rest. You don't need to resolve any of it. The singularity will remain where it is, undefined, waiting for a theory that hasn't been written yet. The event horizon will continue to mark its silent boundary, letting things in, never letting them out. The Hawking radiation will keep whispering away from the darkness, particle by particle, carrying traces of stories no one can yet read. All of it will continue exactly as it is, whether you think about it or not. And it will still be there in the morning. So for now, you can let the questions drift. Let them loosen. Let them move to the background, where they belong for tonight. Somewhere out there, far beyond anything you will ever see directly, that soft ring of light still glows around the shadow, patient, enormous, unchanged. And here, much closer, something equally quiet is happening. Your breath, in and out, steady, uncomplicated. A rhythm that does not need explanation. The universe is vast, but it is also immediate. It is the distant glow of a black hole. And it is the quiet rise and fall of your chest, both at once. Whatever black holes really are, whatever waits at their center, wherever their geometry might lead, they have been there for a very long time, long before the Earth, long before any question was ever asked about them, and they will remain long after, not in a threatening way, just in a steady, continuous way, part of the structure of things. And tonight, in the last quiet moments before sleep, that is a strangely comforting thing to know, that the universe does not need to be fully understood to be real, that it does not need to be solved to be experienced, that it can simply be deep, wide, unfinished. And you, for now, are here inside it. That is enough.